Okay, well today we'll start Unit 8, Introduction to Acid and Bases. And you may have had a little bit of acid-base chemistry last year in first year chem. We're going to use a couple different equations. These are in your equation sheet. Well, the first one is in your equation sheet. pH equals negative log of hydronium. And also lots of individuals write it this way also. Hydronium is technically H3O positive, but lots of people shorten it to H positive. How can you do that? Well, if you take an H positive and add H2O, you get H3O positive. So lots of people consider this and this the same as hydronium. Technically, that's hydronium. We have a couple other equations. These are also in your equation sheet. K, we've had K before. KC, KP, KSP. Well, this one's called KW because it deals with water, and water self-ionizes, and that KW is 1 times 10 to the 14th. So there is virtually no left to right. It does go a tiny bit left to right, but mostly it's right to left. And we can also kind of think about if you take the power of the log of the KW, you would get pKa. If you take the log of the hydronium concentration, you can get to pH, or if you have hydroxide, you can get the pOH. So the same relationship that occurs here. They just are powers of instead of scientific notation with some exponents there. So we have a couple of definitions of acids and bases. And I guess this works for us for the most part. If it has a H positive, and typically that H is going to be found in the front of the molecule, then it's an acid. Unfortunately, there's some acid and bases out there that don't have that H positive, OH minus idea, but they're still acids or bases, so we needed a second Bronsted-Lowry model for acid and bases. And this one's protons. So what is a proton? A proton's really virtually an H positive, because hydrogen atoms have one proton, one electron, and no neutrons. So if it's H positive, it just has the proton. So there's our definitions. And this is going to be a typical idea that there's going to be an acid and a base, and it's going to make two products, and those products, we are always going to attach the word conjugate to them, and one of them is going to be acid, one's going to be a base. We can also talk in terms of their relationships to each other. Let's erase these items that I had, and if you notice, the HA is only one H positive away from the A minus, and the H2O is only one H positive away from the H3O positive. The items that are one H positive away from each other are pairs. And one will be an acid, the other one will be a base. If it's on the left-hand side, acids and bases. If it's on the right-hand side, conjugate acids and bases. So let's try to figure those out. You can start anywhere here, doesn't matter. I think it's easy to identify the acid in this case. And by the way, if you say A, that's universally known in these questions as the acid. If that's the acid, the other item has to be the base. What is HF related to? It's related to F minus. So there's your conjugate base. And then we don't really have much left here to pick from. Ammonia is the base, so ammonium is the conjugate acid. And They have to be one H positive different from each other. The one that has the one more H positive is the acid component. The one that has the one less is the base component. I think HCN would be the easiest one maybe to identify, although I guess OH minus is fairly easy to identify too. So conjugate base, conjugate acid. Remember, conjugates are on the right side. Don't use the word conjugate for anything on the left-hand side. So HCN is related to CN minus. So if HCN is the acid component, then the CN minus has to be the base component. And then it's never acid reactions. It's never base reactions. It's an acid-base reaction. So you've always thought of water as being neutral. Well, we'll come up with definitions of what neutral means in a little bit, but in this case, water is an acid. Okay, a couple other ones here. In organic chemistry, we also learned that COOH, that is a acid. So that's a carboxylic acid. Acid, if that's an acid, the water has to be a base. Well, wait a minute, we just made water an acid in the previous question. Well, in this one, it's a base. And by the way, a little misprint there, that should be H3O positive. So those two are very much related. And then these are related. So we had one question where water was an acid, and we had one now that water is a base. So that's going to be interesting. We'll get a definition of that kind of material in a second here. Ammonia, we know from the previous slide that was a base. So ammonium has one more H positive, so it's the acid component. And then here is our conjugate acid, and whoops, I was going to put conjugate. I don't want to do that. That's our base. So we did talk about water, and water is called an amphoteric substance because it can act as an acid. Maybe we'll call this one the acid, and we can call this one the base. So if it acts as an acid or a base, it's amphoteric. If the Kw is 1 times 10 to the 14th, we could kind of talk about ICE tables. 0 plus x is x, 0 plus x is x. So that's that. So that means x equals 1 times 10 to the 7th. And they would both equal that. So that is the definition of neutral, that they have to be the same concentrations. If the H positive is greater, it's acidic. If OH minus is greater, it's basic. We've always attached it to pHs below and above 7. No, it's whichever concentration is greater. Okay, so the rest of these I think are going to be mathematical. We have our equations. So this one, what's the concentration of OH minus? So we have 1 times 10 to the negative 14th equals hydronium times hydroxide. Hydronium is given, and hydroxide was not given. So we'll solve for hydroxide. And that is a much bigger number than the hydroxide number, so it is acidic. We have ammonia, and we have a hydroxide concentration, and this time calculate H positive. So it's very similar to our last question. We don't know H positive, but we do know the hydroxide. And this is going to be a tiny number. So 10 to the negative 12th, that's tiny. So this time we got basic. The hydroxide is the bigger of the two numbers. Now here's an interesting question. So I told you that if you change the temperature, you don't have the same kW. This time it's 1 times 10 to the negative 13th. So these two values will still be identical because it's like IC table, 0 plus x is x, 0 plus x is x. But the K is not the same as it was in our last question. And for the purposes of this question, I'm going to leave it as that. And the reason I would be leaving it as that, we're going to get into these in a second, but I think it'd be a good opportunity to do this now. If we were told to calculate pH of this. So negative log of 1 times 10 to the negative 6.5 would actually be 6.5. So you would think, 6.5, that's below 7, it's acid. But it is not, because the hydronium and the hydroxide both equal the same value. So it's actually a neutral substance with a pH below 7. So if you change the temperature of your water, you can actually make it look like it's an acid or base without actually being acidic or basic. I'll use Le Chatelier's principle to figure out, is this endo or exothermic? So if we put energy over on the left-hand side and talk about that at a higher temperature, you end up getting a higher concentration. So the only way that's going to happen is if you put energy on the left-hand side. More energy is going to be able to break the bonds that hold the H's and O's together in H2O. So, endothermic. Okay, so I gave you a sneak peek of the pH equation. We could also do the same thing with POH. So you have some options when we get to questions. You can either go from pH to POH with hydronium and hydroxide concentrations, because we all also know the KW equation, or pH plus POH equals 14. And for all these questions, unless told you otherwise, we're going to assume 25 degrees Celsius. Okay, this one does not require any calculator. So we'll do POH first because the hydroxide's given. So if you would plug that into your calculator, the log of 1, that's not gonna help us out. But the log of 10 to the negative third is negative 3. That negative 3 and the negative that's in the front of the log will cancel each other out, so we'll be left with an answer of 3. Now, question raises, well, what do you do with significant figures and decimal places when you're going back and forth between these kind of questions? And the measurement, the concentration has one significant figure, meaning that the pH or POH should have one decimal place. So there is the correct answer for the POH. And I don't even know that you need to show this mathematically, but pH is POH plus pH. I'm sorry, pH plus POH equals 14. So if I do 14 minus 3, I would get 11.0 for the pH. Okay. We have distilled water. We have 60 degrees Celsius. We have the hydronium concentration. Previously, I think I had left it as 1 times 10 to the negative 6.5. And we've already mentioned that it has to be neutral because the distilled water is going to have the same amount of H positive and OH minus. 3 times 10 to the negative 7th. We have 2 sig figs here, so we're going to go 2 decimal places. So 6.52, you go, it's got to be acidic. But remember that the hydronium and hydroxide have to be the same in distilled water. So it's not going to be acidic, it will be neutral. We got some rainwater. So now we're going to go and do a little bit opposite from what we were doing in the past. So that has to go in that spot. So that means you have to use the anti-log, and also don't forget about that little negative there. So depending on if you have a grapher or not, or a scientific, to do the function first or the number first, but you need so again, it might be the anti-log button, which is the 10x key, and you need negative 4.82. Again, it might be the number first and then the function, or it might be the function then the number, depending on your calculator. But let's see what we get here. I got that for the hydronium, and then you can do a couple different things to get the hydroxide. I think might be easiest to go like this. There we go. Calculate the pH of that molarity. So, and I take that, I'm not going to keep writing this down, pH equals negative log of hydronium. And when I put that in my calculator, I get an answer of, wait a minute, pH of 9.26, that would mean that by all accounts, that looks like that's going to be a basic solution. So that's not logical. How could you put an acid into water and get a basic solution? Well, here is how this is incorrect. Well, you know what? I'll write that down, calculated. But what you forgot to add was there's always, now we're assuming 25 degrees Celsius, there's always that much hydronium in the water. So if you add that to 5.5 times 10 to the negative 10th, that gives you pretty dang close to that amount, which would be pH that. So sometimes the hydronium that's just in the water because water breaks up a little bit is important. And in this case, it's very important. So 9.26 would not even be in the ballpark of the correct answer. Blood at 25 degrees Celsius. So that's a little bit of an issue, because blood isn't going to be at 25 degrees Celsius. It's in the bloodstream. It's going to be at 37 degrees Celsius. That's normal body temperature. But we have all of our information here to go with 25 degrees Celsius. All of our, 1 times 10 to the 14th for the kW, so forth. So we're gonna assume 25 degrees Celsius. Okay, so we have a pH of 7.41. Well, let's go 14 minus 7.41. That would get you the pOH. I think that would probably be a good place to start. Certainly don't have to do that. That equals 6.59. Okay. To do the pH to hydronium, or the pOH to hydroxide, you need the negative anti-log. So negative 7.41 with an anti-log button would give you 3.89 times 10 to the negative 8th molar. And the hydroxide would give you 2.57 times 10 to the negative 7th molar. Okay. And our last question. And here, this is not always going to be spelled out to you, but you have to be cognizant of this, that if you have some information about pH, we could go from pH to pOH. That's 14 minus the pH. Then you could go from pH to the hydroxide concentration using the anti-log of negative pOH. But that hydroxide is not the same thing as magnesium hydroxide, because there are 2 hydroxides for every 1 magnesium hydroxide. So at the end, to get the magnesium hydroxide, you will have to divide by 2 to get the magnesium hydroxide. Okay, so 14 minus 10.52. What is that? That's 3.48 for the pOH. And then put the negative 3.48 anti-log into your calculator, and the hydroxide concentration is 3.31 times 10 to the negative 4th molar. To get the magnesium hydroxide, you need to divide that number by 2. So stoichiometry seems to never kind of go away permanently here. And that's it for today.